The National Electrical Code, or NEC, provides guidelines for transformer bonding, specifically addressing how to ensure electrical safety and compliance. Section 250.148d of the NEC focuses on transformer secondary conductor bonding. This section stipulates that the secondary conductor or conductors of a transformer must be bonded to the transformer enclosure to one or more equipment grounding conductors or to one or more grounding conductors. Furthermore, the code mandates that a bonding jumper shall be connected between the transformer secondary conductor or conductors and any accessible terminal in the transformer secondary circuit external to the enclosure. Now, let's consider a scenario where an inspector requests bonding to both building steel or UFA ground into a cold water pipe. The NEC requirements generally allow for bonding to either building steel or a cold water pipe, not necessarily both. Therefore, the inspector's request might be seen as more stringent than the minimum NEC requirements. It's crucial to understand that the NEC does not explicitly require bonding to both building steel and a cold water pipe. However, an inspector might interpret the code in a way that necessitates additional bonding for enhanced safety. In such instances, it becomes important to clarify the reasoning behind the inspector's request. So, what approach can you take to resolve this discrepancy? Firstly, engage in a discussion with the inspector. Explain your understanding of the NEC requirements and provide reasons why you believe that bonding to either building steel or a cold water pipe should be sufficient. Reference the specific section of the NEC, which is 250.148d, to support your argument. Secondly, review the local authority having jurisdiction, or OJ regulations. Some local jurisdictions may have additional requirements for transformer bonding that go beyond the NEC. Contact your local building department to determine if there are any specific regulations that need to be met in your area. These local rules can sometimes be stricter than the national code. Thirdly, consider the option of bonding to both building steel and a cold water pipe. If the inspector remains firm on their requirement for additional bonding, you might consider this as a compromise. Bonding to both systems will satisfy the inspector's request and provide an extra measure of safety and compliance. It is important to note that electrical systems rely on effective grounding and bonding to ensure safety and prevent electrical hazards. Grounding provides a path for fault current to return to the source, allowing overcurrent protection devices to operate and clear the fault. Bonding connects non-current carrying metal parts of the electrical system to create a low impedance path for fault current. In general electrical terms, grounding relates to connecting the electrical system to the earth, while bonding involves connecting various metallic parts within the system to ensure electrical continuity and safety. Grounding typically involves connecting the neutral point of a power system to the earth through a grounding electrode system. This establishes a reference point for voltage and provides a path for fault currents to flow back to the source. Bonding, on the other hand, is the practice of connecting all non-current carrying metal parts of an electrical system together to create a low impedance path for fault current. This includes items such as metal conduits, enclosures, and equipment frames. Effective bonding ensures that if a fault occurs, the fault current will quickly flow back to the source, tripping a circuit breaker or fuse and energizing the circuit. Understanding the specific requirements for grounding and bonding is crucial for electrical safety and compliance with the NEC and other applicable standards. The NEC provides detailed guidelines on how to properly ground and bond electrical systems in various scenarios. Now consider common grounding and bonding methods. Several methods are used to achieve effective grounding and bonding in electrical systems. These include using a grounding electrode system, which typically consists of one or more grounding electrodes such as ground rods, ground plates, or underground metallic water pipes. The grounding electrode system is connected to the electrical system through a grounding electrode conductor. Another method is using equipment grounding conductors, which are used to connect non-current carrying metal parts of equipment to the grounding system. Equipment grounding conductors can be wires, metal conduits, or other approved means. Another method is using bonding jumpers, which are used to connect different metal parts together to ensure electrical continuity. Bonding jumpers are typically used to bond metal conduits, enclosures, and equipment frames. The size of grounding and bonding conductors is determined by the size of the overcurrent protection device protecting the circuit. The NEC provides tables that specify the minimum size of grounding and bonding conductors based on the rating of the overcurrent protection device. Maintaining electrical continuity is crucial for effective grounding and bonding. Electrical continuity refers to the uninterrupted flow of current through a conductor or a system of conductors. In the context of grounding and bonding, electrical continuity ensures that fault current can flow back to the source without encountering high resistance. High resistance in the grounding or bonding path can impede the flow of fault current and increase the risk of electric shock or fire. Electrical continuity can be verified using a multimeter or a continuity tester. These devices can measure the resistance of a conductor or a connection to ensure that it is within acceptable limits. The NEC requires that grounding and bonding connections be made in a manner that ensures permanent and effective electrical continuity. In some specific applications, there could be more specific nuances. In healthcare facilities, for example, electrical safety is of utmost importance due to the presence of sensitive medical equipment and vulnerable patients. The NEC provides specific requirements for grounding and bonding in healthcare facilities to minimize the risk of electrical shock and ensure the proper functioning of medical equipment. One important requirement is the use of isolated power systems in critical care areas. Isolated power systems are designed to prevent ground faults from interrupting the power supply to critical equipment. Another requirement is the use of equipotential grounding, which involves bonding all exposed metal surfaces in a patient care area together to minimize voltage differences. Now let's consider industrial facilities. Industrial facilities often have complex electrical systems with heavy machinery and equipment. The NEC provides specific requirements for grounding and bonding in industrial facilities to ensure the safety of workers and the reliable operation of equipment. One important requirement is the use of a separate equipment grounding conductor for each circuit. This ensures that fault current has a dedicated path back to the source, minimizing the risk of electric shock. Another requirement is the use of ground fault protection for equipment, which is designed to detect and interrupt ground faults before they can cause damage or injury. In hazardous locations, such as areas where flammable gases or vapors are present, electrical safety is of paramount importance. The NEC provides specific requirements for grounding and bonding in hazardous locations to prevent explosions and fires. One important requirement is the use of intrinsically safe equipment, which is designed to operate safely in hazardous locations without producing sparks or excessive heat. Another requirement is the use of explosion-proof enclosures, which are designed to contain any explosion that may occur within the enclosure. Finally, let's remember that grounding and bonding requirements may vary depending on the specific application and the local AHJ. It is essential to consult the NEC and local regulations to ensure compliance with all applicable requirements. Working with a qualified electrical contractor can also help ensure the grounding and bonding systems are properly designed and installed. The principles of grounding and bonding in electrical systems are fundamental to ensuring electrical safety and preventing electrical hazards. Grounding provides a path for fault current to return to the source, while bonding connects non-current carrying metal parts to create a low impedance path for fault current. Understanding the specific requirements for grounding and bonding is crucial for electrical safety and compliance with the NEC and other applicable standards. Now let's delve more deeply into the specifics of transformer grounding and bonding. Transformers are a critical component of electrical power distribution systems, used to step up or step down voltage levels to meet the needs of various loads. Proper grounding and bonding of transformers is essential for ensuring safety and preventing electrical hazards. The NEC provides detailed requirements for grounding and bonding transformers, covering various aspects such as the size of grounding conductors, the location of grounding connections, and the types of grounding electrodes that are permitted. One of the key requirements is that the secondary winding of a transformer must be grounded if the voltage exceeds 150 volts to ground. This requirement is intended to limit the voltage to ground and reduce the risk of electric shock. The grounding connection must be made at the neutral point of the secondary winding or at a point on the secondary winding that is electrically equivalent to the neutral point. The size of the grounding conductor must be based on the size of the secondary conductors, as specified in the NEC. In addition to grounding the secondary winding, the transformer enclosure must also be bonded to the building grounding system. This is typically accomplished by connecting a bonding jumper from the transformer enclosure to the building steel or to ground bus. The bonding jumper must be sized according to the NEC and must be installed in a manner that ensures a low impedance path for fault current. In some cases, it may be necessary to provide additional grounding electrodes for transformers, particularly in areas where the soil resistivity is high or where the building grounding system is inadequate. Additional grounding electrodes can help to reduce the ground resistance and improve the effectiveness of the grounding system. When installing grounding electrodes, it is important to follow the NEC guidelines for electrode spacing and depth. The NEC specifies the minimum spacing between grounding electrodes and the minimum depth at which they must be buried. These requirements are intended to ensure that the grounding electrodes are effective in providing a low impedance path to ground. Another important aspect of transformer grounding and bonding is the proper selection and installation of grounding connectors. Grounding connectors must be listed for the purpose and must be installed in accordance with the manufacturer's instructions. The connectors must be properly torqued to ensure a secure and reliable connection. Over time, grounding and bonding connections can corrode or loosen, which can compromise the effectiveness of the grounding system. It is important to periodically inspect grounding and bonding connections and to tighten or replace any connections that are found to be loose or corroded. Regular maintenance of the grounding system can help to ensure that it remains effective in protecting against electrical hazards. In addition to the NEC requirements, there may be local codes or regulations that govern transformer grounding and bonding. It is important to check with the local HA to determine if there are any specific requirements that apply to your installation. Compliance with local codes and regulations is essential for ensuring the safety of your electrical system. In summary, proper grounding and bonding of transformers is essential for electrical safety and compliance with the NEC and other applicable standards. The NEC provides detailed requirements for grounding and bonding transformers, covering various aspects such as the size of grounding conductors, the location of grounding connections, and the types of grounding electrodes that are permitted. By following these requirements and performing regular maintenance of the grounding system, you can help to ensure that your electrical system is safe and reliable. Electrical inspections play a crucial role in ensuring the safety and compliance of electrical installations. During electrical inspection, a qualified electrical inspector will examine the electrical system to identify any potential hazards or code violations. The inspector will typically check the grounding and bonding system to ensure that it is properly installed and maintained. If the inspector finds any deficiencies in the grounding and bonding system, they will typically issue a notice of violation and require that the deficiencies be corrected. It is important to promptly address any deficiencies identified during an electrical inspection to avoid potential safety hazards and to ensure compliance with the NEC and other applicable standards. Electrical inspectors are trained to interpret and enforce the NEC and other applicable standards. They have a thorough understanding of electrical safety principles and can identify potential hazards that may not be obvious to the untrained eye. Working with a qualified electrical inspector can help to ensure that your electrical system is safe and compliant. To ensure compliance and address concerns, a collaborative approach involving discussion, review of regulations, and compromise is often the most effective way to resolve the issue while maintaining safety and code compliance.